Okay, in this part we shall be studying about the properties of DTFT. The properties of CTFT and DTFT are almost quite similar, so I will go through it faster. So let us go to the first property, which is the linearity property. So if x of n gives us the discrete time Fourier transform of x e to the power j omega, and y of n gives us the discrete time Fourier transform of y e to the power j omega, then the property of linearity essentially states that if the input is the weighted sum of these two signals x of n and y of n, the output will also be the weighted sum of their individual responses. Mathematically, if z of n is equal to ax of n plus by of n, this will give us a Fourier transform pair of z e to the power j omega, which is equal to ax of e to the power j omega plus by of e to the power j omega. So this is our linearity property, and we shall try to prove the property using the synthesis and the analysis equation. So we know that from the equation of z direct transform e to the power j omega is equal to summation of n, which goes from negative infinity to infinity, z of n e to the power minus j omega n. Now in our case, z of n is equal to ax of n plus by of n times e to the power minus j omega n, where the limit goes from negative infinity to infinity. Now, collapsing these two parts, we can write n, which goes from negative infinity to infinity. A, since it is not dependent on n, we can bring it out of the summation operator, x of n e to the power minus j omega n plus b summation of n, which goes from negative infinity to infinity, y of n e to the power minus j omega n. So this is also the direct transform of x of n, x of e to the power j omega. So this can be written as x of e to the power j omega, and this term over here can be written as b y of e to the power j omega. So we have established that the Fourier transform of this expression over here is this one. So from this we can tell that the linearity property will hold true for every DTFT pairs. Now moving on to the next property, which is our time shift property. The time shift property where it is if x of n is having a DTFT pair of x of e to the power j omega, then if we shift x of n by a time n naught, that is z of n is equal to x of n minus n naught, that is x is shifted by a value of n naught, this will give a Fourier transform of x e to the power j omega times e to the power minus jn omega naught, which will be equal to z of e to the power j omega. Now, we know from the direct transform equation e to the power j omega is equal to summation n goes from negative infinity to infinity z of n e to the power minus jn omega, and z of n is equal to x of n minus n naught e to the power minus jn omega, where n goes from negative infinity to infinity. Now, if we consider n minus n naught to be equal to m, it is also true n will be equal to m plus n naught. And when n approaches negative infinity, now taking out a small amount of value from negative infinity will not change the value of infinity, and so m will also be negative infinity. If n becomes infinity, m will also become infinity. So replacing these values in the equation, we get z of e to the power j omega equal to summation, now in this case m, which goes from negative infinity to infinity, x of m e to the power minus jn m plus n naught. Now expanding this term, we can write summation m, which goes from negative infinity to infinity, x of m e to the power minus jn m times e to the power minus jn this will be j omega, this will be omega, j omega m, this will be j omega n naught. Now, since e to the power j omega n naught is not dependent on the summation variable m, we can bring it out of the summation operator. So e to the power minus j omega n naught times summation m, which goes from negative infinity to infinity, x of m e to the power minus j omega m. So upon closer inspection, this is identical to the expression of the direct transform, where the function is x of m and the variable is m instead of n, as we have seen earlier. But changing the variable doesn't essentially change the direct transform equation. So this can be written as e to the power minus j omega n naught times x of e to the power j omega. Hence, once again, we have established that the Fourier transform of this expression will give us e to the power minus j omega n naught times x e to the power j omega n naught, which is our time shift property. Now we move on to the next property, which is the frequency shift property. Where if x of n gives us a Fourier transform pair of x of e to the power j omega, then suppose z of n is equal to x of n times e to the power j omega naught n, will give us a Fourier transform pair of x of e to the power j omega minus omega naught, which is equal to z of e to the power j omega. So what I am trying to say is that if there is a shift in the frequency by a value of omega naught, there will be a change in the time domain. That means the time domain expression will be multiplied by e to the power j n times the shifted value, which in our case is omega naught. So let us try and establish the proof. So z of e to the power j omega will be equal to that we get summation n, which goes from negative infinity to infinity, z of n times e to the power minus j omega n, which is the equation for direct transform. Now this in turn can be written as summation of n, which goes from negative infinity to infinity. Z of n is replaced by the given expression x of n times e to the power j omega naught n times e to the power minus j omega n. So z of e to the power j omega, multiplying these two expressions, we get summation x of n e to the power minus j omega minus omega naught n, where the limit goes from negative infinity to infinity. Now, since we know that from the direct transform equation, x of e to the power j omega will be equal to summation, where n goes from negative infinity to infinity, x of n e to the power minus j omega n. Now, since in this expression x is essentially a function of omega, so we have written x as a function of e to the power j omega. But in this case, z is a function, x is a function of omega minus omega naught. So this in turn will become z e to the power j omega, which equals to x of e to the power, instead of j omega, omega has changed to omega minus omega naught. So this will become omega minus omega naught. So there is clearly a shift in the frequency domain. So we have established the Fourier transform of this expression to be the shift in the frequency domain. Now moving on to the fourth property, which is our scaling property. Now the scaling property says if x of n gives us a Fourier transform pair of x e to the power j omega, then if z of n is a scaled version of x of n, which is multiplied by a scaling operator p, will give us the Fourier transform pair z of e to the power j omega, which is equal to x of e to the power j omega by p. That means if a signal is contracted or collapsed in the time domain, it will be extended or expanded in the frequency domain. Now let us go to the proof. We can write from the equation of direct transform z e to the power j omega to be equal to summation, where n goes from negative infinity to infinity, z of n e to the power minus j omega n. Now plugging in the value of z of n, we get summation of x of np e to the power minus j omega n, where the limit goes from negative infinity to infinity. Now if np is equal to m, then obviously n will be equal to m over p. And when n is approaching to infinity, n if approaches infinity, multiplying any number with infinity will essentially give us infinity. So m will also become infinity. And if n approaches negative infinity, m thusly will approach negative infinity. Now changing the variable n in this equation, we get z e to the power j omega to be equal to summation, where m goes from negative infinity to infinity, x of n e to the power minus j omega m by p. Now bringing this p and dividing omega by it, we get m, which goes from negative infinity to infinity, x of m e to the power minus j m omega over p. Now comparing this with our direct transform equation, which states that e to the power j omega will be equal to summation of n, which goes from negative infinity to infinity, x of n e to the power minus j omega n, the variable have changed from n to m. But this doesn't matter in our case, because whatever might be the variable in the time axis, the Fourier transform in this case, in any case, whatever the variable, the Fourier transform will remain same for all. But what we are concerned is that omega in the frequency domain has changed to omega over p. So if this gives us the Fourier transform of e to the power j omega, this expression will give us the Fourier transform of x of e to the power j omega over p. I hope you understand that, because since the value of omega is changed to omega over p over here. So we have seen that x of np will give us a Fourier transform pair of capital X e to the power j omega over p. So this is our scaling property. Now moving on to the fifth property, which is the frequency differentiation property, which states that if x of n gives us a Fourier transform pair of x of e to the power j omega, then say z of n be a signal which is equal to jn x of n, will give us a Fourier transform pair of z of e to the power j omega, which is equal to d omega of x of e to the power j omega. That means if we are to take the derivative of the Fourier transform in the frequency domain, we have to multiply the time domain by a value of negative of jn, which was negative of jt in case of our continuous time Fourier transform. Now we know from the direct transform equation, x of e to the power j omega is given by summation where n goes from negative infinity to infinity, x of n e to the power minus jn omega. And now differentiating the left hand side with respect to omega, we can write dd omega of x of e to the power j omega, which is equal to summation of x of n, which goes from negative infinity to infinity. And since x of n is not dependent on the variable omega, we can bring it out of the differential operator as well, and the remaining will be dd omega of e to the power minus jn omega. Now differentiating e to the power something, we get n goes from negative infinity to infinity, x of n. So e to the power minus jn omega, when differentiated with respect to omega, will be e to the power minus jn omega, which remains as it is. And as per the chain rule of differentiation, we need to differentiate this term over here, and differentiating j and omega in terms of d omega, we get negative of jn. Now in this expression, since n which goes from negative infinity to infinity, we just bring these two terms together, x of n minus jn e to the power minus jn omega. Now comparing this equation with the equation A, comparing with A, say this be B, comparing B with A, we have seen that the value of x of n here is changed to x of n times minus jn. So if x of n gives us the Fourier transform of x of e to the power j omega, and x of n times minus jn gives us a Fourier transform of dd omega of x of e to the power j omega. So quite evidently we can write z of n to be equal to minus jn x of n, or otherwise x of n times negative of jn will give us a Fourier transform pair of dd omega of x of e to the power j omega. So this is our frequency differentiation property. Okay, now the next property, that is our sixth property, which is the convolution property. Now, as for the convolution property, in an earlier video I have said that if two signals are convoluted in the frequency domain, the result will be such that the signal is multiplied in the time domain. That means if two signal is multiplied in the time domain and the resultant signal is Fourier transformed to another signal, this signal will be representing if the Fourier transform of the signals are convoluted in the frequency domain. So the converse is also true, which means if two signals are multiplied in the time domain, if two signals are convoluted in the time domains, the resultant signal will have a Fourier transform such that the signals are multiplied in the frequency domain. So, if x of n gives us a Fourier transform pair of x of e to the power j omega and y of n gives us a Fourier transform of y of e to the power j omega, then say z of n is equal to x of n convoluted to y of n, and z of n in this case will give us a Fourier transform of z of e to the power j omega, which will be equal to e to the power j omega times y to the power y e to the power j omega. So as I have said before, if these two signals are convoluted in the time domain, the frequency domain representation will be such that if we take the frequency, the Fourier transform of x and the Fourier transform of y and multiply it, this will give the Fourier transform representation of the convoluted signal. So let us move forward and prove the property. So z of e to the power j omega can be written summation of negative infinity to infinity x of n, z of n e to the power minus j omega n, where this is the direct transform equation. N goes from negative infinity to infinity. We replace the value of z of n by this value, x of n times y of n e to the power minus j omega n. Now expanding this a bit further, z of e to the power j omega will be equal to summation of n goes from negative infinity to infinity. Now as per the definition of convolution, this can be mathematically written as summation of k, which goes from negative infinity to infinity, x of k times y of n minus k e to the power minus j omega n. So this formula you have seen in the section A part, where two signals when convoluted in the discrete domain, this is the mathematical expression for that. Now if n minus k is equal to m, then n will be equal to m plus k. And when n approaches negative infinity, taking out a certain amount from negative infinity doesn't change the value, so m will also approach negative infinity, and when n approaches positive infinity, m will also approach positive infinity. So now changing the variable in this expression, we get summation of n which goes from negative infinity to infinity, and since x of k is, first of all let us rearrange this summation operator. This can be done without changing the value. The summation of k which goes from negative infinity to infinity, and since x of k doesn't depend on any variable n, so we can bring that out as well, and the remaining remains as m which goes from negative infinity to infinity. So you have changed n minus k to m, y of m e to the power minus j omega m plus k. Now expanding this to term k, which goes from negative infinity to infinity, x of k, and we bring out e to the power minus j omega times k outside of this summation operator, e to the power minus j omega k. Then the summation y of m times the remaining value e to the power minus j omega m. This is m, which goes from negative infinity to infinity. Now then, this is the direct transform of x of e to the power j omega, and this expression is the direct transform of y of e to the power j omega. So we have seen, rather established, that if two signals are convoluted in the time domain, the frequency domain response will be the multiplication of the two signals. So this is our convolution property, and with that let us go to our penultimate property, which is the seventh property, the time reversal property. Time reversal property, which states if x of n gives us a Fourier transform pair of e to the power j omega, then if x is reversed in the time domain, that is, x is folded along the y-axis in the time domain, the frequency response will also be the same, e to the power minus j omega. The frequency response will also be folded along the frequency domain. So here x of n yielded a Fourier transform of e to the power j omega. X of negative of n will give us a Fourier transform of e to the power negative of j omega. So suppose this is z of n and this is capital Z of e to the power j omega. So from the direct transform equation, e to the power j omega can be written as summation n, which goes from negative infinity to infinity, z of n e to the power minus j omega n, which can be written as n, which goes from negative infinity to infinity, x of negative n e to the power minus j omega n. Now if minus n is equal to m, then n will be equal to negative of n will be equal to negative of m, and if n approaches infinity, m will be approaching negative infinity, and if n approaches negative infinity, m will be approaching positive infinity. So replacing this, the variable in the Fourier transform expression, we can write z of e to the power j omega such that m goes from positive infinity to negative infinity. See, the limit has changed. X of negative of n e to the power minus j omega n. Now there is a property in the summation operator. This limit can be changed without changing the essential result of this summation, and this can be simply explained that if we are to sum numbers, say x1 plus x2 plus x3 plus dot 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 up to infinity, we can add from 1 to 2, then 2 to 3, 3 to infinity, or we can add from infinity backwards. The result doesn't vary the result will not vary. So we can change the limit easily, and this becomes m, which goes from negative infinity to infinity, x of minus n, sorry, this will be negative of m e to the power minus j omega negative of m, and taking this negative value to this omega, m, which goes from negative infinity to infinity, x of n negative n e to the power, I'm sorry, this will become m, since we have changed the value of x of m power minus j minus omega m. This is the Fourier transform of x of e to the power minus j omega. Comparing it with the direct transform gives us for the value of omega, and since omega is replaced by negative omega, the direct transform value will be replaced by negative of j omega. So this is our time reversal property. With that, we come to our very last property, which is the property, or which is not a property per se. This can be stated as a theorem, and you have guessed it right. It is the Percivals theorem. So, what is the Percivals theorem? The Percivals theorem states the energy signal where n goes from negative infinity to infinity, x of n will give the value 1 over twice pi integration of negative pi to pi summation of x e to the power j omega whole square d omega. So this is the energy signal, this is the power signal, that power spectral density. So Percival theorem essentially derives a relation rather for the energy signal and its power spectral density. Now from the left hand side, we can write summation n, which goes from negative infinity to infinity, x of n whole squared can be written summation of n, which goes from negative infinity to infinity, x of n times the conjugate of x of n. Now from the inverse transform equation, we know that x of n is equal to 1 over twice pi integration of negative pi to pi x of e to the power j omega times e to the power j omega n d omega.